Good morning, everyone. My name is Divyam Sharma, and my registration number is 23BC1510. I am a student of VIT Vellore, Chennai branch. Today, I am here to present a fascinating topic that bridges the gap between theoretical computer science and real life communication systems, applications of finite automata in a network. Finite automata may seem like abstract machines from your theory class, but they play a surprisingly practical role in how network function may secure and ensure smooth communication. In this presentation, we will walk through what finite automata are, why they are used in networking, their role in protocol design, packet filtering, intrusion detection, QoS, and even routing. So let's dive in. Finite automata. Finite automata are abstract machines used to recognize patterns in input sequence, forming the basis for understanding regular languages in computer science. They consist of states, transition, and input symbols, processing each symbol step by step. If the machine ends in an accepting state after processing the input, it is accepted, otherwise, it is rejected. Finite automata has four types: finite state automata, push down automata, linear bound automata, turning machine. Why finite automata in networking? Because predictability and consistency. Finite automata provide a step by step structure, making network behavior reliable and error resistant. Efficient protocol design, FA module protocol steps, example TCP handshake, ensuring correct standardized connection. Real-time security used in packet filtering and intrusion detection by machine traffic pattern to block malicious data. Traffic management QoS. Finite automata help prioritizing data, ensuring critical data. Example video calls gets bandwidth priority. Error detection. Finite automata support error detection algorithm like CRC to identify transition error quickly. What are its applications? Finite automata play an essential role in networking by providing structured, state-based model for various processes in data communication, protocol handling, and network security. Following are the some applications of finite automata in design: protocol design and verification, packet filtering and deep packet inspection (DPI), instruction detection system (IDS), traffic shape and quality of service QoS, data compression and error detection routing algorithms, protocol design and verification network protocols. Protocols are set of rules governing how data is transmitted, received, and acknowledged across network. They handle everything from setting up communication like TCP three-way handshake to managing errors, ending connection, and maintaining data integrity. Role of finite automata. Finite automata represent each step in a protocol as a state and each action, like sending or receiving data, as a transition. This allows the protocol to be structured by a series of rules and states that devices follow to ensure orderly communication. By using finite automata, each step in a protocol sequence is explicitly defined, so the protocol can reliably enforce rules and manage errors if any states does not progress correctly. Example TCP handshake. TCP connecting connection states. The TCP three-way handshake, which involves SYN, ACK, and ACK messages, can be broken into states. Listen, the server waits for a connection request. ACK is acknowledgement. Example TCP handshake, connection state. The TCP three-way, uh, which I told, listen, the server awaits for a connection request. SYN sent, the client sends an SYN packet moving to the SYN send state. SYN received, the server receive SYN, respond to SYN ACK, and transition to SYN receive. Established. When the client sends back an acknowledgement, both enter the established state and data can now be exchanged. Benefits. Modeling these steps as finite automata ensure that each device follows the handshake sequence correctly. Any deviation, like the ACK packet appearing without ACK SYN, breaks the sequence, preventing potentially harm or misconfigured connection. Packet filtering and deep packet inspection. Packet filtering basics. Routers and firewalls use packet filtering to examine packets as they pass through the network. Each packet header contains fields like source, destination, IP, port number, and prototype type. Packet filtering is typically the first line of defense in the network security. Finite automata and packet filtering. FA helps match packet data against predefined rules. Each state in the FA could represent a specific filter criterion, example, a source IP, and transition between states represent matches as those criteria. The automation examines incoming packets, transition through states if the packet data matches the rule, and ultimately decides whether to follow or block the packet. Deep packet inspection (DPI). DPI involves inspecting packet payloads in addition to header. This allows detection of specific content, example a virus signature or unauthorized content, making DPI crucial for network security. In, in DPI FA process packet content, checking for specific byte pattern or sequence. For example, certain payload patterns might match a known malware signature, causing a DPI system to drop the packet and raise an alert. Example, virus detection. A virus may have specific type byte pattern that it leaves in the payload of a packet. FA can represent the packet as states, matching it against incoming packets. If the FA reaches the final state in the pattern, it signals a match, blocking the packet to prevent infection. Intrusion detection system. What is IDS? An IDS monitors network traffic for unusual or unauthorized access patterns, which may indicate malicious activity. IDS often operate on preset attacks pattern or signature. Finite automata in IDS. Finite automata helps IDS recognize suspicious patterns like the scams or attempts to exploit known vulnerabilities. Each step in an attack is represented as a state in the FA, allowing IDS to match patterns step by step. For example, a brute force login attempt involves multiple failed logins in which IDS can track using FA. After detecting several login attempts, the FA transition to state representing a possible brute force attack triggering an alert. Example, SQL detection attack. SQL injection involves inserting malicious SQL code like DROP tables using a query to manipulate databases. FA in IDS can detect by looking for typical SQL injection pattern like uh, dash dash or drop. The FA moves through state as it sees this character reaching an alert state as the sequence completes. Traffic shaping and quality of service (QoS). Traffic shaping overview. The traffic shaping is used to prioritize or limit traffic type. Example, prioritizing video calls or large file downloads to optimize data with usage. Finite automata in traffic shaping. Finite automata are configured with policies defining priorities for different traffic types. Each type of traffic is represented as a state and FA transition guide decision on how much bandwidth each type can be used based on current condition. Quality of service QoS. QoS prioritizes high demand application like voice or video over non-urgent traffic like email or file transfer. It allows system to manage these priority dynamically. If video starts, FA can enter the high priority state for video, ensuring low latency and high bandwidth allocation. Example, if streaming video, an FA could monitor network load and quality needs to needs for a video stream. If bandwidth increases, the FA might switch to an lower quality video stream, thus preventing buffering. Data, compri- data compression and data detection. Data compression. Compression techniques like Huffman coding and run length encoding are often used to reduce data size. These methods allow efficient transmission by encoding frequent patterns with shorter codes. Finite automata in compression. In Huffman coding, each symbol has a binary code based on frequency, with shorter code for more frequent symbol. FA decode Huffman code by matching each bit in encoding message to state in the automation. Error detection with CRC. Cyclic redundancy check involves appending a check sequence to the end of the message. FA will data received by recalculating the CRC and comparing it to the transmitted one. Example, run length encoding. RLE comprises repeating characters. Example, A becomes 5A. FA tracks repetition and encode them efficiently, saving space and improving transmission speed. Routing algorithm. Routing algorithm basics. Routers use algorithm to find optimal paths for data packets. Two common algorithms are distant vector routing, example RIP, and linked state routing, example OSPF. Data Finite automata and routing. Finite automata helps track each routing decision as a state with transition representing path changes based on updated network information. Distance vector routing. FA helps router adjust path decision when neighboring routers update their distance figure. Linked state routing. FA handles linked state advertisement from other routers to build an updated map of the network. Example, distance vector routing. A router using FA to represent paths to each destination. If a new code with lower cost appears, the FA transitions to route state, optimizing network efficiency. Advantages: network efficiency. FA perform matching and transition operation quickly, ideal for real-time package processing and filter. Predictability and reliability. Finite automata structured approaches ensures predictable outcome, making them suitable. And this, I finish my presentation. Thank you so much for your time and attention. Finite automata provide a solid structured foundation for various essential functions in networking, from protocol handling and security filtering to routing decision and data compression. Their ability to operate based on well-defined states and transition makes networks predictable, source, and efficient. Thank you.